Hello everyone, in this video we're going to pick up where we left off in section 9.10, which is Taylor and Maclaurin series. So subsection 2 here is a little bit different from subsection 1. In subsection 1 we were given a function and we said, hey, find the Maclaurin series or find the Taylor series. Now what we're going to do is we're going to use this list of a bunch of different known Maclaurin series for different functions that we're very comfortable with, and then we're going to use this list to determine power series for other functions by the operations of addition, subtraction, multiplication, division, differentiation, integration, and composition. Right? So we can use all of those operations on these functions here, and therefore on these power series over here, to find different power series or Maclaurin series for functions. All right, so the first example here, find the Maclaurin series for the following function. Right, so the first one we're going to look at is cosine of radical x. So if we notice, looking at this list, we don't have cosine of radical x, right? But we do have cosine of x, right? And if I look at cosine of x, I could replace radical x in my series 6 there, and then that would give me a formula for cosine of radical x. So we're going to replace x with radical x in formula number 6. Right? So I get cosine of radical x is equal to, and for these, I'm going to do it 2 different ways. I'm going to do it by looking at plugging in our values into the big long series, and then I'm going to look at plugging it into the formula, and I'm going to show you that you can do it either way. So first, because it's a little bit more intuitive of what's going on, let's plug it into the big old series. Right? So I get 1 minus, and now instead of x, I write radical x squared over 2 factorial plus radical x to the 4th over 4 factorial minus radical x to the 6th over 6 factorial plus radical x to the 8th over 8 factorial, and so on. So now I need to simplify this so I'm able to write a formula. So radical x I can always rewrite as x to the 1/2, right? So I'm going to do that in each one of these cases. So instead of writing radical x, I'm going to write x to the 1/2, so that way I can more easily see what I need to do to simplify these powers of x. So now I'm taking powers to a power, right? I'm taking x to the 1/2 to the squared power. So if I take x to the 1/2 to the squared power, remember, what do I do when I take powers to a power? I multiply their powers, right? So in other words, I'm going to multiply 1/2 times 2. 1/2 times 2 is just 1, right? So I get x over 2 factorial. And now I multiply 1/2 times 4, which is going to give me 2. So I get x squared over 4 factorial minus 1/2 times 6 gives me x cubed over 3 factorial plus 1/2 times 8 is 4, so x to the 4th over 8 factorial, and so on, right? And again, now I need to write my formula, right? So this is n equals to 0, n equals to 1, n equals to 2, n equals to 3, n equals to 4. And so I need to write my formula here. So again, I don't like the first term, or maybe even the first 2 terms maybe not help, but looking at like maybe the second and third term, I noticed that the powers of x are exactly n, right? Well, actually, let's do the sign of them. The sign for the odd indices is negative, so I know I want -1 to the n, because if I take -1 to an odd power, it's going to be negative. And then I want x to the n, because I want my powers of x are exactly equal to my indice. And then, oops, this should have been 6 factorial. And now I got to think about how I get my denominators. Well, my denominators are just going to be 2 times n factorial, right? Careful with your parentheses, right? Because 2 times n factorial is different than 2n factorial. This time we want 2n factorial, right? And so this is my formula. So that's where I can do it term by term. I can also do it just by looking at my formula, my summation formula that I have for number 6 as well. So more concisely, cosine of radical x. Now let's go ahead and just plug in radical x into the formula given for cosine, right? The formula given by cosine is -1 to the n over, now instead of x, I write square root of x to the 2n over 2n factorial. Right, and now I simplify this. Well, once again, I'm going to simplify the square root of x with x to the 1/2 power. And now if I take 1/2 and multiply it by 2n, the 2's cancel out and I'm just left with x to the n. So I get the sum from n equals 0 to infinity of -1 to the n over x to the n over 2n factorial. And notice that's exactly equal to my formula up here, right? So I can do it term by term, or I can do it by looking at the terms and simplifying everything out, right? Either are fair game. Okay, so now let's look at b, f of x equals ln of 1 plus x. So we're going to need number 3 here. So I'm just going to go ahead and pull it down here, so that way we have it on hand. Okay, so looking here, we want to replace 1 plus x, or we want to place x with 1 plus x in formula number 3, right? So I get ln of 1 plus x. And now here, what am I going to get? I'm going to go ahead and do the long way first. So I plug in 1 minus x, or 1 plus x for x. So I get 1 plus x minus 1 minus 1 plus x minus 1 squared over 2 plus 1 plus x minus 1 cubed over 3 minus 1 plus x minus 1 to the 4th over 4, and so on. And notice in each one of those cases, the 1's cancel out with each other. And I end up getting x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and so on. And again, I need to write my final formula. So this one we can start anywhere. And this time it's actually going to be more convenient. Well, actually, it's going to be more convenient to start at n equals to 1. If you started at n equals 0, that's fine. You would still have, you end up getting the same formula. It would, you just have to do a little bit of algebra. Okay, so if we start at n equals to 1, then how do we get our powers of x? Well, our powers of x always look like x to the n, right? And I guess always first I should do my signs, my SIGN signs of this. So when I have even values for n, I get negatives, right? So in other words, what I need to have here is -1 to the n plus 1 power, right? So that way the evens have negative signs and the odds have positives, right? And then I want x to the n over n. If I had started out with n equals to 0, then I would get, if I start out with n equals to 0, again, this would be completely correct. I just know that it's going to be easier to start out. It's going to be prettier to start out with n equals to 1. But if I start out with n equals to 0, it would be fine. And what would end up happening is I would need -1 to the nth power, because in that case, the odd powers or the odd values of n are the ones that get negatives. And then I would need x to the n minus 1 over n minus 1, right? And again, that's a little bit uglier, but it is exactly equal to the formula that we had. But since it's a little bit uglier, that's why I said we should probably start at n equals to 1. But again, both of these are equivalent to each other. Oops. Sorry, I gotta fix it. So this is our formula for ln of 1 plus x. So now we can also do it the quick way, right? More concisely by just looking at the formula. So ln of 1 plus x is equal to, looking at our sum here, n equals 1, negative 1 to the n plus 1, and then now I'm going to plug in 1 plus x minus 1 to the n over top of n. And now again, I see that the 1's cancel out. I'm left with the sum from n equals to 1 of negative 1 to the n times x to the n over n. And notice that is exactly the same as what I got up when I did it the long way. All right, how about sine of x squared? So for sine of x squared, I need to look at the sine formula. So looking at the sine formula here, put it up top. So here I'm going to replace x with x squared in number 5, right? So this looks like sine of x squared. This one, we can maybe save ourselves a little time and just do it the fast way, all right? So doing this, I end up with the sum n equals 0 of negative 1 to the n, and now I'm writing x squared to the 2n plus 1 power over top of 2n plus 1 factorial. And if I do that, I end up getting negative 1 to the n over x. Remember, when I take power to a power, I am multiplying. So I multiply 2 times 2n plus 1, which gives me 2n. This would work. There we go. 2n plus 2 over top of 2n plus 1 factorial. And you can do it the long way to check and make sure you get the same answer, but as always, you will. Okay, so now let's look at this one here. We want to find the first 3 non-zero terms in the Maclaurin series, e to the x times tangent inverse of x. Right? The first 3 non-zero terms are going to be like the x term, the x squared term, and the x cubed term. Right? So I need to take e to the x and multiply it times tangent of x. So I'm going to grab both of those here. So e to the x is this guy. And tangent of x we need as well. Tangent of x is this one. And I'm going to go ahead and cut that. Okay, so if I want to find e to the x times tangent inverse of x, which is what the question asks, I need to take e to the x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. And I need to multiply that, move this over a little bit, multiply that times x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9, and so on. And what am I doing? I'm multiplying these, and when I multiply these two factors, remember I multiply term by term. I multiply, like if I had 1 plus x times x squared plus 5, what would I do? Well, I would take first term times first term times second term times first term, right? I'd FOIL it. Same idea goes here. I need to FOIL this, but just with more. So I need to multiply 1 times every single term, right? Then I need to multiply the second term here by every single term. Then I need to multiply the third term by every single term. Oops. And then finally the fourth term by every single term. Right? Oops. So this is the idea here, is I'm just FOILing out these terms and multiplying. Okay, so when I take the first term of the first big parentheses and multiply it times the second big parentheses, it'd be 1 times all of that. So I'm just repeating everybody on the right. So it'd look like x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7th plus x to the 9th over 9 plus, and then it would go on forever. And then I pick up with multiplying by the second term of the first group of parentheses, right? And if I multiply this second term times everybody over here, then I'm just going to bump up the power of x by 1, right? So here I'd get x squared minus x to the 4th over 3. Oh, that's not working right there. X to the 4th over 3. Why is that not working there? Plus x to the 6th over 5 plus, or minus x to the 7th over 7 plus x to the 10th over 9, and so on, right? Then I'd multiply the third term by everybody. And in that case, I'm just going to multiply x squared, so I bump the power by x by 2 and multiply by 2 factorial in the denominator, right? So I'd end up with x cubed over 2 factorial, just 2 factorial, then minus x to the 5th over 2 factorial times 3 plus x to the 7th over 2 factorial times 5 minus x to the 9th over 2 factorial times 7 plus x to the 11th over 2 factorial times 9, and so on. And remember, what was I trying to do? Find the first 3 non-zero terms. Well, the first term, the smallest power of x I see is going to be x squared. So then I would need, or I'm sorry, not x squared, x, and then I need x squared and x cubed. So in this term here, I know that when I look at the oranges start with x cubed as their lowest power, right? And so now when I go to do the purple, when I go to multiply the next one, the purples, I know my first term is going to be x cubed times x, in other words, x to the 4th. And every other term after that, if I would multiply it from the first parenthesis to the second one, then I would always end up with a power bigger than x cubed, right? So it won't affect finding the first 3 terms. So I'm going to do the next one just for fun, but I actually don't even have to do it, again, because its first term is going to be x cubed, right? So now I take x cubed over 3 factorial and multiply it by everybody on the right. So I get x to the 4th over 3 factorial minus x to the 6th over 3 times 3 factorial plus x to the 8th over 3 factorial times 5 minus x to the 10th over 3 factorial times 7 plus x to the 12th over 3 factorial times 9, and so on. And this is what I was trying to tell you, is now when I go to do my next term, it's going to be x to the 4th over 4. When I go to multiply it by x, I know I'm going to get x to the 5th, which is not going to be one of the first 3 terms, right? So it's not adding to the first term. So that's why I don't have to continue marking anymore. Okay, so again, the first 3 non-zero terms are going to be x, x squared, and x cubed, right? So I find my x squared is going to be here, and there's no other x squareds. Then my x cubed is going to be this one. There's no x cubed in the blue, and then there's an x cubed in the orange, and there's no x cubed in the purple, right? And there would be no more x cubed left in it. So now, just identifying all these terms, I would get x plus x squared plus, and then now I have the coefficient of negative 1/3 and the coefficient of positive 1/2 times x cubed, right? So maybe I should not skip that step. Maybe I'll write out all the steps here. I would get minus x cubed over 3 plus x cubed over 2 factorial. And then again, I only wanted the first 3 non-zero terms, right? So I'm just going to write dot, 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 because we know there's going to be a bunch of these terms here, but the question didn't ask for those. So this would be x plus x squared. And again, now I factor out a x cubed. So I get negative 1/3 plus 1/2, because 2 is the same as 2 factorial x cubed. And that gives me x plus x squared plus 1/6 x cubed, and so on. So those are the first 3 terms, multiplying it out. If you had to divide terms, like in your homework, I think maybe you have to, the same thing would happen, right? We would just divide just like this, where we do a foiling, but in the division case. Okay. Finally, find a power series for sine x squared. Okay, so again, at first glance, you may not think, you may not realize how to proceed, because maybe we take sine and we square it, but then that's going to be really tricky, because that means we take this guy and multiply it times itself, and we just did that with either the x and tangent x example, and it's obviously not very easy. But, well, actually, that's the sine inverse, so I'd have to take the sine one and square. But I actually can make my life a little easier by looking at the trig identity that sine squared is equal to 1 minus cosine of 2x over 2, which is the same as 1/2 minus 1/2 times cosine of 2x. So what does that mean? That means I can look at cosine, plug in 2x, then I can multiply it times 1/2, and then I can subtract that from 1/2, right? So now I need to look, this is telling me that I need to look at cosine in order to find this guy. So let's go back up here. Let's look at cosine. So cosine is right here. So I'm going to plug 2x into number 6. So if I did that, I would get cosine of 2x. In this case, since we've got a lot of different steps, we're going to plug cosine, we're going to plug 2x in, multiply it times 1/2. It might actually be easier to just do the long way, and that's how we're going to do this. So this will look like 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial plus 2x to the 8th over 8 factorial, and so on. Now I can get rid of this. So now we should simplify this. I get 1 minus, remember when I'm taking 2x all to the squared power, I need to square both the 2 and the x, right? So this looks like 2 squared over x squared over 2 factorial plus, now when I take everything to the 4th power, again I take both terms, so I take 2 to the 4th power times x to the 4th power over 4 factorial minus 2 to the 6th power over 6, or I'm sorry, 2 to the 6th power times x to the 6th over 6 factorial plus 2 to the 8th, x to the 8th over 8 factorial, and so on. So that's what cosine of 2x is, but remember, what do I need for my formula? I need negative 1/2 times that, right? So then, negative 1/2 times cosine of 2x looks like negative 1/2 times all of that I just found. right? So times this, because this is what cosine of 2x is. Right? So I can scooch this over a little bit. So I need to distribute this 1/2, this negative 1/2, to every single term. If I do that, I get negative 1/2. The negative sign with the next term is going to make that term positive. And then one of these 2's cancels out with one of the 2's in the numerator, right? The 1/2. So I end up with 2 to the first power x squared over 2 factorial. Now, when I go to this next term, the negative sign with the 1/2 is going to make it negative. So in other words, all my signs are getting flip-flopped, right? Because I'm multiplying by negative 1/2. And I lose a power of 2 in the numerator because of one of the 2's that's in the denominator by the 1/2. So this ends up being 2 cubed x to the 4th over 4 factorial. This ends up being plus 2 to the 5th x to the 6th over 6 factorial plus, minus, because remember I switched signs, minus 2 to the 7th x to the 8th over 8 factorial, and so on. And we're almost there, right? Last thing we need to do is 1/2 minus all of that. So in other words, now we take, if I want 1/2 minus 1/2 times cosine of 2x, it would just be 1/2 plus all of this, right? Because we already took care of the minus part here. So I just, because the first sign is minus, I can just keep all this, and that's what I get here. So if you notice, the first 1/2s are going to cancel out, and I'm left with 2x squared over 2 factorial minus 2 cubed x to the 4th over 4 factorial plus 2 to the 5th over, times x to the 6th over 6 factorial minus 2 to the 7th x to the 8th over 8 factorial. Got a little ugly there. Oh, it's because of the 7. Plus, and so on. And now we need to finally write our formula, right? So this is n equals to, we'll start maybe 0, n equals to 1, n equals to 2, n equals to 3. And now we should write our final formula. So, positive powers, even powers, or even values for n give us positive. So in other words, I need -1 to the n. And then I would need to go 2 to what power I want odd powers. So in order to get the 3, I'd need to take 2 times 1 plus 1. In order to get to the 5, I need 2 times 2 plus 1. So this is always going to be to the 2n plus 1. X. Now I need to get squared. I need to get to there. So I would need 2n plus 2. Right? Because maybe looking at this term, I would get 2 times 2, which would be 4 plus 2. Look at this time, 3 times 2, which would be 6 times 2. All over top of that power. The denominator is the same power, that 2n plus 2 factorial. And that's actually kind of ugly, but that's what we got. If I wanted the same formula starting at n equals to 0, I could do that as well. I'm sorry, starting at n equals to 1. Maybe this will be prettier. I don't know off the top of my head. What would this one look like? This one would look like, okay, now I would need -1 to the n plus 1 because the evens have the negative sign. And I would need 2 to the now let's see, I'd want to have (2n minus 1), right, for that power. So that one's getting a little bit awkward. 2n minus 1. And then x to the 2 n over 2n factorial. All right, so it really looks like either formula, whether I start at n equals 0 or n equals to 1, is going to give me a similar formula. Right? But this was a case where I looked at sine squared, I rewrote it, and then I had to do some different algebra knowing about cosine of x. All right, that's all I have for this video. Thank you.